Okay. Do we start?
Let's go.
Okay. So today I will talk about the restriction and globalization of partial dynamical system, and then I will talk about the topology in partial dynamical system. This corresponds to chapter 3 and 5, respectively, of Excel's book. So this document that I prepared is a mixture between some parts of Excel, some comments that I have added, and I have also removed some parts of Excel's book. So let's review it. So first we will start with the restriction and globalization. As we see here, and this is what Marius actually said last time, that in order to build a partial action, it's enough to consider a global partial action and restrict it to a domain that may not be invariant via the partial action. As we see in this figure, we have X here, and if we act with a partial action eta, the image may escape, and so these are the only elements that we will like to preserve. And one quick note that, well, we will define this D sub G, the domain, as the action, the global action that we have acting on X intersected with X. And note here that we have this, that the global action acting on the D of the inverse of G coincides with the domain of G. And this is true because eta is a global action, yeah? And so both eta sub G and eta sub the inverse of G are both bijective and inverse of each other, and both of them have the complete space as their domain. However, if eta was not a global action but partial, this expression may have some problems. And the first that we see is immediate, that X may not be fully contained in the domain of the action. And so this might not be well defined. But if we interpret this in a more open sense, a less restrictive interpretation, this quality still holds. Here I want to give an example. Consider eta the C partial action over this semi-grid. This is the Diego's action. The vertical shift in 1 unit. And I will consider 0 to be natural. And let X be this subset. So just the first 3 lines somehow. So D of -2 will be only C times 0. And have some comments? Team 0. And D2 will be C times 2, right? And here we get this equality, right? If we act by 2 over here, we get here. That's what we want in partial actions.
And it is probably easy to guess that D-1 and D1 are composed of 2 horizontal discrete lines, if I'm not
right.
wrong.
Right. And so what I want to comment here is that this is seen because, like, well, this expression is fast because these actions are global bijections, say somehow, but a partial action is also somehow a partial or a local bijection. So it behaves well when it can, right? So we will not have problems of having contentions here. We will have the equality. And this is a comment that I want to make. This is good in which sense? Because we are studying this new category that's composed of partial actions, and we want this category to have a good hierarchy, just as we have with groups and topological spaces. All those we know, we want to can say this one is bigger than this other one, we can compare some of them. And so we would like the restriction of a restriction to be still a restriction, right? And the comment that if we restrict a partial action is give us immediately that result. So we have that behaves good in the sense of the category of partial actions. But I want to make a comment here that I'm not sure that all of these quote unquote smaller partial actions come from the existence of a restriction. I remember the example we told last week as well, that we have this shift in two units that was smaller in the sense that we had the G equivariant map, but it was not, at least from the beginning, a restriction of the original partial action. And so in this fashion, we consider theta sub G as we know it should be in the notation of Diego, and it will be the restriction of this, that's our original global action. And this easily defines a partial action. And well, that's, I want to make the comment that my numeration here is according to Excel's book, just in case any of you want to check something in comparison with that book. Well, and here's the interesting part, that it's immediate from this definition that under these conditions, the inclusion of X into Y is actually a G equivariant or covariant, as we have called it, map, right? And why? Because this was Diego's definition, right, of equivariance, right? And in this case, this X2 will be our wider space. And so all of the domains are the complete space. So this makes no problem. And theta behaves exactly as eta whenever it can. So this equality also holds easily. Just note that usually we want X not to be Y, because if not, it's a trivial example. And then this partial action morphism, the equivariance, is not an isomorphism in this category. So I wanted to make a quick note that with these partial actions, we have built the graph of the partial action, and the graph also behaves well with restriction in this sense that if we have a global partial global action, to find the graph of the partial action, we just have to find the intersection between X, G, and X again, right? Recall that the graph was defined as this, right? So the element that goes from here, there, as usual in groupoids. And as again, as theta behaves equal to eta, this proposition follows.
And the graph of theta is probably our best example. It was the example introduced several times, for example, by Diego. It was called transformation groupoid, a groupoid canonically associated to a classical action, to a global action.
Yeah.
And we will see that it is already quite obvious that we get other graphs by restriction. And be careful, it is not a restriction as I told you 2 days ago. It is not restriction to an invariant set.
Yeah.
So what I defined, and is still very useful, is somehow more particular than what we do here. And restricting at the level of dynamical systems, or restricting at the level of the corresponding groupoids, which are the graphs, commute. It is what you wrote, at least at the level of sets, this equality. Actually, you can verify that the smaller one is a subgroupoid of the other, and later on it will be probably a nice topological set, probably a closed subset, and so on and so forth.
And I just wanted to comment that here, one of the questions that we stated last time is that what does happen when can we have empty domains? And from here, it's obvious that yes, we can, because it's just enough X to not be to don't overlap with its image under some G.
And in your particular case, already D3 and D minus 3 are void.
Yeah, exactly. So now we started with this one structure, and we know that we can go to smaller structures, right? And as usual, we would like also to know if we can build bigger structures. So we want to take a partial action and guess if does it exist a global action such that these partial actions correspond to an interesting subset, right? So for this, we will consider a global action eta, yeah, and suppose that it does exist, yeah, and that theta is the restriction to X. And then we will consider the orbit of X, and this may be a bit confusing because I'm using orbit indiscriminately, but remember that we have two actions playing game here. The global one, that's eta, and the partial one, that's theta, right? So eta, we will consider all the images of X under eta, yep? And that is what we will call the orbit.
Yes, but be careful. Usually people in dynamical systems are calling this object differently. For example, they say it is a stabilizer of X, or maybe
Okay.
it is a saturation of X, even more often. Actually, it is a union of orbits for all the points belonging to X. But most of the people would not call this an orbit. We can do it, of course, and we understand what's all about. It is somehow the smallest invariant set associated to X.
Exactly.
Invariant.
So,
this is
yeah,
why you call it a saturation.
exactly. That's what's interesting. That X, this orbit or this saturation, will be eta invariant, right? So even in the bigger action, we have eta invariance, and the restriction of eta to this orbit will be another global action, yeah. And if that global action will restrict it again to X, we will gain again our original partial action. How can we have this in mind? Just remember again our example that plane or typical example, it behaves in two dimensions. So if we just add a third dimension up and make the same, just the same, we now, instead of moving up a square, we move a cube. Then this is another global action considered in the space of C3, and it's bigger. So it contains, as a smaller partial action, the one we have over the plane. But it's way too big, right? The elements of X do not reach those that are above or below. It just reaches its own level. So we will not be interested in all these big structures, but the ones that are big but not that big. So the definition, the formal definition would be that let eta be a global action of G on a set Y, and theta be a partial action obtained by restricting eta to a subset X. So if the orbit of X coincides with Y, we will say that eta is a globalization or an enveloping action for theta.
So this definition tells you the intention of the author. The author would like to extend, if possible, his partial dynamical system, but in a minimal way, in the most economical way. Because obviously to make it too large would be spurious, it would be difficult to communicate to the others. How large did we do it? Just imagine that you start with a global dynamical system, and you want to extend it to a global dynamical system. The single obvious and canonical way is to leave it alone and to not to change anything, which will be a very simple particular case of what you will tell us. It is unuseful for such things to make it twice as big, to add extra dimensions,
exactly,
and so on and so forth.
And here I wanted to make this comment that this should somehow recall what we understand in topology as a completion, in the sense that we know that there are several complete topological spaces that include a certain space or an isomorphic copy of it. But when completing, we care especially about those in whom original space is dense, because we are looking for a bigger structure, but not that big. Yep. And actually, the proof of the following theorem that most certainly we can guess what it should be.
Sorry, Nestor. This economy principle is present everywhere in mathematics, not just in topology, or let's say in set theory, because you are doing just set theory here. You have set into, maybe into a very large vector space, you would like to take the space generated. So when you say generated in a certain sense, it implies that what you generate is a nicer structure, but the smallest possible one. Exactly. So this happens everywhere, algebraically, topologically, in all senses, you are interested in the smallest good one.
Exactly.
Yeah. Okay.
So the theorem is what we expect, that every partial action admits a globalization, and which is unique in the category of global actions. How? In the sense that if we have two globalizations, then we have an equivariance, an equivalent equivalent map, right? Such that it coincides with the identity of X on X. Remember that each one of these contains a copy at least of X. And here I wanted to comment that this uniqueness is somewhat better than the one we have in topology, for example. Because even if we forget homeomorphism, a completion is not unique in the topological usual sense. For example, the real line can be completed with 1 or 2 points, right? So in this case, our bigger and minimal structures is unique in this category. It's very good. And here again, I want to make the comment about our, as I call it, the mother of all of our examples. And again, recall a doubt that we had last time, that if for that particular partial action, we could see the global action that was hidden. We were wondering if does it always exist? So this this theorem say that yes, we can always find that bigger structure. So given the partial action, we will build this equivalence relation that's in the usual fashion when we want to find these bigger structures. Yeah. In G times X, given by if X corresponds to this domain, that's equal to this, right? And if this composition, it takes X into Y. So this is somehow calling that the converts the points, and it's a part of the groupoid. So, well, this is just checking from the definition. It's easy to see that it's symmetric and reflexive. And using Diego characterization, we can see that it admits the transitivity. And with Diego characterization, I mean what he stated about the composition in partial actions. And this again somehow recalls what Marius said last time, that this expression was easier to verify. Like, and this is what we use when we want to prove things. Recall that there wasn't a specific definition of what we wanted in for two objects to be composable, but we said that this was easier to see.
So if
So
I understand well, you are trying now to construct the bigger space, isn't it?
yeah,
So the bigger space should be, I try to guess it. Actually, I don't know what the construction is, but indeed you have to put somewhere as basic information, both the group and the space X. On the other hand, they are not independent. They are related somehow by the fact that they were connected by the partial action. So probably the real space is a sort of quotient modeling, codifying in a certain sense the connection between the two, reducing somehow the space. Probably if the action is trivial in some sense, and I can imagine such a thing, probably you will really get a product. But since there is information inside the connection of the two spaces, you put them together to give you a chance to have a large object, but the quotient will take into consideration what we already know. This means the action theta.
yeah. For example, I will want the dots of here, like here. I will want one point to be connected to the next point that it will fall in one unit going down. So that exists, and there are lots of pair of points that are connected in such way. And then I want that to be what's the name, the equivalent class. And so consider that going down, it's also an object. And so I will construct not just the semi-grid that we have originally, but I will be able to go even down. So as Marius was saying, we will naturally take the quotient of G times X under this equivalence relation. And we will denote Gx, the equivalent class, right? Mm-hmm. So we want X to be included in this quotient, and we have this inclusion, and we may easily identify X with this image under this I, right? So I want this expression I want to define now the global action. Yeah, and it should be what we want it to be. So a global action of a certain object G acting on this pair.
Just a moment, Nestor. Since I still try to digest the equivalence relation, which is very important. Mm-hmm. So can you show us again the definition? It is after assume that. No, earlier, this one.
The definition of what?
The definition of the equivalence relation. This
one is
this snake. Okay, let me see. So I have a couple of points, a pair of points G and X, and another one H and Y. How can I describe the connection? So first of all, I see that X and Y should belong to the same orbit. Maybe some of the words are not exact, they are metaphors. So they are connected by a transformation. So they belong to the same orbit of the partial transformation. On the other hand, if theta would be a global action, the final equality in this definition could be written as theta g of x is equal to theta h of y. Because for global actions, theta of a composition in the group is a composition of the two transformations. And if this is true, because theta h minus 1 is the inverse of theta h, I can put it in the right-hand side. So if I will forget the definition, I will think that I have two elements, x and g, which arrives in the point theta g of x, and another couple of points, y and h, such that under h, y is transformed in another point. And the equivalence means that the 2 points are the same. You arrive in the same place. On the other hand, this should be done in a more sophisticated way because it is not true that theta distributes correctly, rigorously to the 2 points. And this is a good version, and we can check that it works okay. But actually, instead of G and X, I should think of the final result of having them together. I think of theta G of X, which should be equal to theta H of Y. This is equivalent somehow. And it is probably easier to remember. But of course, this is more sophisticated because some things cannot be done if the action is only partial. Okay, thank you.
And for example, if we take the 1x, the class of the element 1x will be something like g theta g of x, something like that, right?
Yes, so you go along the orbit.
Yes, you go along the orbit of every.
But you don't take the entire orbit.
Exactly.
You go from one point to the other.
Other way.
You take into consideration the element of the group which sends you from one point to the other. So it is just a couple of points on the orbit and not the entire orbit.
Yes, in that way you can put x inside this class easily.
And exactly that's what we will care, because somehow here there's hidden theta 1, right? So I want then to define a global action, but this inverse is what will not always be true. But I can put it in the other side. Let us see how we will define the global action.
Yes, but once again, sorry for interrupting you so much. So it is important to note that not just you have 2 points on the same orbit, but you also have the way to go from one to the other. Because if you don't, the entire class would be an orbit. And in this way, instead of defining a larger space than X, you will define a smaller one, which is the orbit space, the quotient by the of the dynamical system, which is smaller and not larger. So you need this extra variable, which is G or G times H minus 1 to enlarge things and to take into account how you go from X to Y. So finally, the space, even after making the quotient, will be larger and not as an orbit space formed in which each element is an orbit, which is smaller. Okay, thank you. And my wife told me last time not to interrupt you so much. So I still have the right ones to interrupt you.
No, more. So our global action that we will define on this quotient will be given by this. So I want to take a pair, the class of the pair hx, and just what it should be, we should multiply by g, yeah? And this goes to another class, right? But here, if we had another element, another representative of the class, it's under this categorization, if we had here another like ky, then, and we put the g acting, we will have gk acting on y, and it will be just adding here the theta sub k, right? And it behaves good with this relation. And we claim that here the tau acting on x, recall that this is the copy of x that we have on this quotient, intersected with the x, right? It's equal to the inclusion of the domain of G given by the partial action, and this belongs to the X normal, like the original space. And what this tells us is that actually the tau is actually a globalization of theta, our original partial action. Recall that this is what we ask for the domain to be. So in fact, an element of the form 1x, right, lies here if and only if this, right? there is a G here acting.
I'm sorry, is X tilde? It's hat instead of X prime there? Or it's...
This X?
No, I'm sorry, I just... No. Nothing.
Okay.
No.
Okay. So, yeah. But this is so if and only if X belongs to the domain, right, of G, and moving by G minus 1 X, we arrive to Y, this expression. Is it, are we okay with this expression? Yeah, so now I want to verify the other direction, that theta is indeed the restriction of tau to X. Yeah. So we take an element of this domain and we observe that this is related to this object, right? This is what we were telling. From one, this is going to theta G acting on X, and this goes as well from theta G acting on X, right? And so the inclusion, and why I wanted to write it in this way, because the inclusion only tell us how it behaves with this kind of pairs, right? When the first one is a 1. So the inclusion of this object will be this pair, and as they are related, it will be the same equivalence class, and it will be the action of tau on here, right? Which is tau in a composition composed with the inclusion. So we have the equality of compositions, which basically tell us that theta behaves in the same way as tau whenever they can, and in the corresponding spaces. Yeah. So now what the author wants to check is that this globalization is actually unique in this category. So we consider another globalization, eta, that has a domain Y, and it defines this map. Yeah. So yeah, it says that from on this space, on G times the globalization, the original we had, we can send it to eta of G acting on this element. And what do we have? That this phi of G times X, and this will be equal to H times Y, if and only if their images with their corresponding element of the group are the same, which is the same to say this one. Yeah, and here I can actually put eta in the other side, because here we are thinking that they are globalization, so these are global actions. So if X is here, it's the same as this domain for definition, because this is the object we have, and Y is there, right? So this means that Gx, the pair Gx, is related in our original relation with H and Y. So so this map it behaves good with this quotient. And if Y is a globalization, it coincides with the orbit of X under eta, right? So this phi with hat will be an surjective, right? Remember that this one, the original, was here. I think this should be, no, that's right. That's okay. Yeah. So, so then we make the quotient and we arrive here. And well, this says that this is actually a bijective map. And it, well, here the author says that it leaves to the reader to check that the G with the phi with the hat is G equivariance, and it corresponds corresponds to the identity in the copies of X. But I think it's easy to see, just because they both behave the same. This is the idea that's behind. Both eta and tau behave in the same way in X. And X is not that different from the whole space. So the objects that are not on X can be seen like an action of the original partial action of an element of X, the image under this action. And in the global sense, that action can be seen backwards. So if they are the same on X, then they have to be the same in the complete space.
I complain about something. There is a tilde over Y in the formula, short formula describing phi tilde. And it should not exist.
Yeah, I think it should not exist.
I think that this is why, because if not, I will ask you who is
what Y? Is why? Yeah, yeah, because Y is. Yeah, I will fix it later.
Okay, I understand. So it seems to be okay. The idea was to produce a good definition for the larger space and to take very well into consideration both X and G and the action. If somebody wants to understand even better these things, he should do, or she should do, the following exercise. He should apply this definition on a particular case, seeing exactly what the quotient mean, what the equivalence relation mean. This means just take Diego's first example, initial example, Z acting on a half plane, and try to see how this construction with a certain reinterpretation can be understood as completing the half plane to a whole two-dimensional plane. And probably this is possible. Or to change slightly the example, think of a group as R2, for example, or Z2, acting partially on any of its subset. So take a subset which is the interior of a circle or a half space or anything. So try to see if this abstract construction gives you a concrete way to see how you complete the disk to an entire bidimensional plane or things like this. I hope it is possible, because if not, there is a certain schizophrenia. Here you produced a very general and abstract proof. On the other hand, in many situations, as you said, it is rather obvious how to construct one representation. Actually, you got an equivalence class of globalizations, but very often one of them, salta a la vista, it can be constructed directly. And this should be seen also in the proof and not just a posteriori, looking that you've got the abstract object and see that it is isomorphic to the concrete one. Just look at the proof. When you did the equivalence relation, what does it mean in the entire plane, which is the globalization of the half plane? You understand what I would like to, we cannot do it now, obviously, but this should help you to remember the proof and to understand better. Okay, so we have the purely set theoretical result.
Yeah. So
I have a question. I'm not seeing right now, but what happens if I globalize a globalization? It stays the same, right?
yeah,
Should
because like
stay the same, but
from
why?
the yeah, that and that's a good comment on what Mario said. So if you make this construction and we start with a global action, then this exactly becomes that G takes X to the exact same place where H takes Y. Yeah. So then I will make a quotient here, and I will have that this relation that I had original that I can say here it's similar, but I can state that it's actually an equivalence on the quotient. Always states with a 1 in the group coordinate, right? So to say it somehow, if I can always take in this case H to the other side, then all the equivalence class do have a representative that it's stated as 1
Okay.
in pair with the element of this space.
Which finally should lead to a bijection between X itself and X tilde.
Right.
Yes.
Because you...
No, I was thinking that because of this typo that was in the function 5, because I thought that maybe it's easier to build the G equivariant function. So, because go down a little bit, please. A bit more.
Here.
There. You have 5. Then it could be easier to build this phi tilde function if we just identify y with y tilde there. That
Yeah, no, but I
was
think
the
that
motivation of my question.
There is no y tilde. It was...
No, I know, but I just said that if we make this relation in y, then we get y equal y tilde.
Right. Yeah.
Then it's maybe it was there just it was easier to.
No, I understand, and you are right, but this was not the reason for the typo. The typo was just because of Excel. A natural would have been X double tilde or X, let's say X hat or X dot, and not Y.
Right.
Because if you put Y, you already change the notation and you don't really want to put a tilde. But previously the tilde meant for everybody a globalization. So this misleads you somehow. But anyhow, the idea is looking at the proof, and if you start with a global action, you will get itself up to identification. And this is okay, because this is what you want to do. And the identification comes from certain formulas in which the representant had a 1 on the first position. And the single important fact was the point X or Y or X prime in the second position. And this gives you bijection between X tilde and X in this case. Okay.
Okay.
So
thank you.
I will fix the typos and see if we find some other and send it later to you. So now we would like to discuss topology here in partial dynamical system. So now we will fix a group and a topological space X. Now we will give a topological structure to our space. And a topological partial action, yeah, so of the group G on the space X is, it must be a partial action, right? Here I want to make the comment to remember that I said before. In partial actions, we care about local bijections, right? As I said it before, and I put it with italic because that's not a formal way to say it. But the partial actions are bijections whenever they can. And we are studying topology here, so we should ask them to be homeomorphisms. And also, as we have comment, we were just studying a set before, but the sets that we care about in topology are the ones that are open. So it's only obvious, and it should be immediate, that uh, for such partial action to be topological, we will ask every domain to be open, and every here I miss sub G to be homeomorphisms, right? And a topological partial dynamical system should be what we understood as a dynamical system, but asking it to be a topological partial action, right? And sometimes the author said that it might be obvious that we are working on this category with topology, so he may drop the topological adjective. And here a comment is that we had two structures before, the group and the set. And on this definition, I have decided to give a topological structure on X. And we may wonder, why? Why not G? And it's a valid question. And the author simply says, I don't care. He says that this might be more complicated. In which sense? That we are going to think about G being a discrete group, and so we will give it the discrete topology in order to make our constructions. But that simplifies all about open sets and continuous functions in that line. If we give G a more complex topology, then our continuity and homomorphisms have to be good, not just for each G, but for both at the same time, right? So in order to avoid that problem, the author says we will just study the case with discrete groups.
And anyhow, this already covers a lot of applications, especially in the direction of C-star algebras. The groupoids you would obtain by such formalism in which G is discrete, the groupoids will be et al., which is good news because plenty of simplifications are right. present, and still you can treat a lot of many interesting examples. On the other hand, I have seen 2 or 3 articles with a general situation. Since there were also C-star algebras, the group and the space were locally compact, a locally compact group and a locally compact space. And this works, but it is more difficult to read. At each point, you have extra continuities to check into the proofs, into the examples. And since, let's say, 2/3 of the nice examples have discrete groups, the author decided to spare your efforts and our efforts of reading the book, and he stick to this. But of course, this is possible if everybody is topological in a more interesting or more sophisticated way.
I just realized that here I have another type, which should be groups and not books. So I want just to state some brief, where was I? No. Points that the author mentions from the previous chapter, the chapter 4, that we accepted to jump. But, well, an inverse semi-group will be semi-group, right? But equipped with this, right? With this other object, we just don't have identity somehow. We will say that given a set X and 2 subsets, if we have a bijection between both of those subsets, that is what we will call a partial symmetry of X. And we will settle the inverse semi-group of all partial symmetries of of a given set, and it will be easily be an inverse semigroup. So those are just some quick notes that the author states in the previous chapter, and he will use here. And this proposition that says that given a group and a set, then if we have a map from G to the this partial symmetries semigroup, this will define a partial action if and only if we have these conditions, which are exactly the characterizations that we establish for a partial action, right?
We established when?
With Diego, in the first time when we defined what it was a partial action.
We did this, I forgot.
Not in this exact same language, but what it says here is that, well, here we don't have an inverse, right? So it's not an inverse because it's not a group. So it says that the inverse will behave as the inverse, right? And the theta 1 will be the identity. So if this function should take the identity of the group into the identity of partial symmetries, which is just the identity. And this guarantees it just is written in two fashions to ensure the symmetry, but this guarantees that what Diego asked for our domains of the compositions.
Yes, but be careful. Although this is quite close to the initial definition of a partial action, it is not identical from two different points of view. First of all, here you have everywhere equalities of functions and not inclusions and extensions of functions. On the other hand, to have this equality, you need protection. And just look at the most interesting equations, which are 3 and 4. A priori, you compare theta g composed with theta h with theta associated to g times h, and they should not be equal because you are coming from a situation which was quite bad. We have seen this. In a previous interpretation, the problem was that restricting conveniently, they become equal. And actually, you restrict one to the domain of the other and they become equal. Here, with being now in an inverse semigroup, you have a different language. And the language of restriction is done by multiplying to the right with certain things. So if you look, theta h minus 1 helps you a lot in the equation 3. Only after you protect your equation with this one, you really have an equality. If you erase it, you will no longer have it. You will be somehow as at the beginning with a certain inclusion. Somehow you should say that the two objects, theta g times theta h and theta g times h, become equal, let's say, shadowed, protected by theta h minus 1, which should be understood somehow as being in the range of this application, which is to the right. And you can interpret the equation 4 in the same type. You have an equality of two objects which are not equal if you project somehow, if you, I don't know, if you restrict to the left in a certain sense. So this is somehow connected to the difference between inverse semigroup actions in which you have always equalities and not extensions. As in our case. In our case, you arrived into the inverse semigroup of partial symmetries of the set X. And here you need to have equalities. Inverse semigroups are weaker than groups, but when they act by equalities of mappings. So this is a different, this is very close to the initial definition of a partial action, but not the same. and it will appear over and over again somehow at the level of Hilbert space representations, where you will have isometries and so on and so forth. So I wonder how the author knows that the proposition is true. He said
This
something.
proposition? No, he proves this one in detail. But as it was part of the 4th chapter, I decided to skip it.
Okay, so if we are curious, we can go to the 4th chapter and we see
and that's the numeration. It's a 4.5.
And it might be useful because you see how a certain type of axioms convert into another type, still close, but different somehow. This should
and also we should look that this is an equivalence. So it's if and only if. So this also characterizes all partial actions, is somehow what it says here.